Aishi, can you hear me?
Yes, sir.
Okay, so we'll resume with the discussion on resonators and complete what we started last time. If we review the things we discussed about the transmission line resonators, I motivated it last time by looking at the impedance of a section of transmission line, which is either shorted or open from the other end, and try to say that, okay, if we can make that impedance versus frequency look like a parallel LC oscillator or a series LC circuit, then essentially it means that that must also be a resonator, right? And the other picture, of course, is we can think of this as a section of medium where waves can propagate, and it has boundary conditions on either side. And if both boundary conditions are reflective, even partially reflective, then you can set up some standing waves like how we understand Fabry-Pérot resonators. So they are both equivalent ways, and at the end of the day, any such resonator can be modeled by a simple LC circuit, either parallel or series. Or when we look at the from the physics side, we can model them as harmonic oscillators. So everything, the approximations essentially are related to how wide of a frequency range around this resonant frequency can these models be applicable. So that will vary from situation to situation, and particularly depending on the line width of the resonator. Usually, if the line width is very small, which means very high Q resonators, then the model is fairly accurate. But as you go away from the resonant frequency, again, how much away is related to the line width. So if you're within one line width, then everything is okay. If you go much further away, then you will see that the transmission line resonator doesn't match the LC circuit resonator's response as you go away from the resonant. And then this is sort of a not really connected to what we're doing now, but there is a further approximation which one does when we write down harmonic oscillators in a physics approach, which is actually something which is often called a rotating wave approximation. And that gives you a more idealized response of a resonator. It is easy to treat in the equations. And that one is also inaccurate if you go away from the resonant frequency. So you have to keep that in mind. It's kind of a strange thing because even if you look at this first sentence in this section, it says, as we have seen, ideal lump circuit elements are often unattainable at micro frequencies. So distributed elements are frequently used. But this also only works at a very narrow range of frequencies. What they are basically trying to say that for any reasonable parameters for L's and C's you might want at microwave frequencies, they might not be ideal at all in any sense. Whereas this is going to be very, very ideal. You will have an effective L and an effective C, which corresponds to that particular resonance. And as we were seeing it last time, yeah, please. So the effective inductance and effective capacitance we get from the model when we convert a transmission line resonator into an equivalent LC oscillator. That is a perfect one-to-one mapping within the small range of frequencies of where we are trying to. So just reminding you of these kind of expressions, and then we'll go back to microwave office. So this one is the case of a shorted. So this is a short here, and it's lambda by 4, or lambda by 2, which is supposed to be like a series LC oscillator. Then you have a shorted lambda by 4 section, it's like a parallel LC oscillator, and this is basically related to whether at resonance you have a pole in the impedance or you have a zero in the impedance. Right? So parallel LC circuit has a pole at resonance because impedance goes to infinity, and a series one has a zero. So that's why we saw that if you have a shorted lambda by 4, lambda by 4 inverts the impedance, so 0 becomes 1 over 0, you get infinity. A lambda by 2 retains the same impedance, so it looks like a series LC. But you can also get a parallel LC circuit by making a lambda by 2, which is open from the same argument. Open is essentially infinity impedance. So there are actually many ways of constructing this. These smallest sections are related to the what we call as the fundamental mode of the transmission line resonation. That's the smallest standing wave we can fit within that. So how does that work? So let's look at this by considering this shorter lambda by 4 line. So this length here is lambda by 4, and we're going to short circuit it this point. So you can think of the short circuit. Now we have to picture this in the wave picture, wave propagation picture, where we say, okay, voltage as a function of position or current as a function of position. Now, because this point is a short circuit, you know that the voltage here, and if we call this point, let's say x equal to 0, is always going to be 0. So and if this side is open, then here the voltage is going to be maximum, or current is going to be 0. And on the other side, the current is going to be maximum. So if I draw, voltage versus x, then I get something like this. So this, if I want to complete the full sinusoidal variation and go for the full lambda, then you can see that it's 1/4 of the wavelength, right? That's why the section is lambda per, and these are also called quarter wavelength resonators or lambda by 4 resonators. So this is the smallest length you can use to create a resonance at that particular frequency. So remember, the length will depend on the frequency, but for a given frequency, the smallest length you can use is a lambda by 4, which is shorted at one end and open at the other end. So it's both the length and also the two different boundary conditions which is allowing you to set this length to get the resonance. The fact that it is there. Now, if this was lambda by 2, then depending on whether both sides are short or both sides are open, your voltage wave will look something like this now. So this is, you can think of this as going from, say here to here, just with the signs inverted. Or if the voltage, if both the ends were short circuited, then your voltage wave will look like this. So 0 here. So this is V equal to 0, V equal to 0. This is V equal to minus V max and V plus max. So that's how you will decide the length. And of course, whether you want to do a short circuit on one end or not, that again is somewhat dependent on the system you're trying to do. So you will see some of these examples later today in actual devices. So both of these type of resonators, which is lambda by 4 short on one end and open on the other end, and lambda by 2 open on both ends, they are both equivalent to a parallel LC oscillator resonance because they both have poles at the resonant frequency. So one other thing we saw was the relationship of what role does the Z0 actually play, right? And the equivalent expressions we found here tells you that the Z0 is basically what determines what the effective L and effective C of the model is. Remember, we are trying to match the curves. We will go back and look at it in just a second. But you will see, and I think last time we were looking at the difference between these two circuits. So we will see this more clearly, that how in practice you can build resonators which which actually look like a reasonable LC oscillator, and then see how we can control the properties. So let me move to the microwave office software.
So,
yeah.
So why do we need transfer and just with last element we will have better frequency effect? Why? And in transfer line, then you have the periodicity which comes with some finite length of the transfer line. But in case of lumped element, you don't have such periodicity.
Yes, the lumped element which I make in microwave office will be perfect, much better than any transmission line resonator. But I mean, this is basically the same point I've been saying all over this class, is that you cannot make an inductor which has a fixed value of inductance and behave exactly like that over a huge range of frequencies, particularly at microwave frequencies. So maybe let me repeat that for a few minutes. Why is that? It's because the size of the inductor which you build is going to become comparable to wavelength. Okay. How does one make an inductor? Typically, you coil some wire. You have seen in your undergraduate labs those big wire. That's because you are making inductors whose values are in microhenry and maybe even millihenry. But you completely forget the fact that between two rounds or two windings of the wire, there is actually going to be a capacitance between those two. That is completely not modeled in your thing because the frequency is so low and the capacitance is so small that 1 over omega c is essentially infinite. So these kind of effects don't matter when omega is very low. But when you come to anywhere above gigahertz, these things start to matter. The finite size start to matter, the connections start to matter. So building an LC circuit using lumped approximations becomes extremely complicated. You have to make them very small, which makes the engineering of that very complicated. In the kind of experiments we do in our lab, we microfabricate them on a chip itself. Can make them quite small. But even then, they will not behave perfectly. So one side example is also related to the amount of loss. So any capacitor typically you will make will have a dielectric between the plates of the capacitor. And it's very difficult to make dielectric which are lossless. Whereas in a transmission line, the dielectric is sort of the substrate itself. That you can make somewhat better because you can use single crystals like silicon or sapphire, which is what we use in our labs. So, but the basic reason is that you cannot make an L which is only an L at high frequencies. It will have some parallel capacitance to it, it will have some series resistance to it. And similarly, you cannot make a perfect C, it will also have an inductor. So we do make these things, but we have to keep in mind that what we design is not exactly what we're going to get. For example, if I make a parallel plate capacitor with 100 micron by 100 micron square plate, and I compute the area, I know the dielectric constant, I know the thickness, I can compute the capacitance as A epsilon naught over B. And that will not match what we actually measure in the experiment. These kind of things can be checked using the finite elements simulation softwares. So that includes the finite size effects as well. What you will see is that the very fact that it's 100 micron by 100 micron means that that piece of metal has some inductance associated. What that effectively means that at sufficiently high enough frequency, that L and the C will resonate to give you a resonance. So you sort of get a free resonator. You're trying to make a capacitor, but you ended up making a resonator. But as long as that resonant frequency is far away, much higher than the frequencies of your interest, it's still a perfect capacitor for your purpose. So that is what this argument given in Kozar also is saying. You just cannot make perfect inductors and capacitors at those times. Whereas a transmission line is very easy to make. It's just a strip of metal. And you're not making any other approximations there. Right? The modeling in terms of its microwave response is complete. We are just saying that near the resonant frequency, there is a simpler model, which is that of an LC circuit with some effective L and effective C. So that's why that approximation is perfect as long as the frequency you're choosing is not too far away from the operating point from the resonant frequency of that resonance. But that's a very natural approximation to make because if you are making a resonator in your experiment, you obviously want to work near the resonant frequency, right? you're not going to be working far away. It's not always true. I can give you an example of one of the experiments we did where you do operate far away from the resonance system, and that has and there's an implication which is related to the fact that the model we use of a simple LC circuit doesn't predict the correct results when the frequency is far away. We have to use a more accurate model. But the softwares like microwave optics or even finite element software, that they can do that. They can give you the correct frequency response. But what you will see now is how that frequency response changes as you go away from the ideal operating. So, this is the other computer, right? You have to give me a minute to quickly together. Let's start with the lambda by 4 at 6 gigahertz. So lambda by 4 is 90 degrees. Leave the characteristic impedance at ohms. I'll put a short circuit. This is what we saw last time. Let me add a graph. So let's first actually look at a very broad range of frequencies so that we can actually see the things we were mentioning about multiple as well. So plotted is magnitude of the input impedance, which of course will blow up, and that's why this graph looks weird. But you can see it first here is at 6 gigahertz, and the next one is at 8. So this is the thing to note because the next boundary condition in terms of the wavelength you can fit with one end shorted and one end open goes straight away to 3 times the frequency. So this is again something specific to a lambda by 4. In lambda by 2, it will just go to double. So here are the two frequencies. So one thing already you can see that for lambda by 4, the second mode is very far away. So in terms of the whether to worry about the second mode, that is already in a very good situation because you have at least for a 6 gigahertz system, you have 12 gigahertz of space between the two. Right? And usually you're going to work with some IQ resonator. It might have a line width of 3 megahertz. So you're very, very safe in that respect. Okay. Now, this is Z in. Right? Now, if you remember what we typically used to study, so maybe let me actually for that make another structure. So now I've made LC oscillator there as well. Let me just change the Z. This one has a frequency at around 5.63 or so when it's going up. But when you are looking at resonators, normally we are looking at the real part of the reflection coefficient, right? So usually in a network analyzer, that's what we measure. Of course, you can convert gamma to Z in, because that's just related by the reflection coefficient formula. Does that make sense? The two are, one can get one from the other. So even though a network analyzer doesn't measure Z in directly, it measures reflection coefficient. But gamma is just Z minus Z naught over Z plus Z naught. And Z naught is known, gamma is known, so you can compute Z. So let's look at the reflection coefficient. And I look at, let's say we look at the real part. So this is around 5.63. Let me just tune it up so that this is also around 6 gigahertz. And I will adjust the frequency range here from 5.5 to 6.5. Adjust the reference value. Right. So remember the discussion from last time. I can look at the full width half max of this, and since this is a totally overcoupled resonator, there is no internal losses. Right? I have not put any losses with the thing. Then those points are basically these two here. So this is 5.844, and this one is 6.161. So it's about 160 plus 160, 320 megahertz is the line width of this resonator. Now, if I add the reflection coefficient for our resonator now, for this one, again, I just plot the real part so that I can compare the two. You see what's happening? Let me expand the frequency a little bit more. 4.48. This response looks extremely broad. What can I infer from that about the lambda by 4 resonator? Note that the maximum value of this this thing is still at 1. This means that there is no loss. I mean, I have not put any loss in the system. The transmission line is ideal transmission line. Somebody apart from Panya has additional knowledge from elsewhere. So what's the obvious interpretation? Well, C is for quality control. C is more for what? Q factor is high.
High quality factor is less.
C is less compared to.
The one.
So whatever C is here, the C for the effective C, which you have not yet looked at, for this lambda by 4 resonator is probably much smaller. So remember, that's the only free parameter in some sense, because the resonant frequency is fixed. If you change C, you have to change the L as well. So both L and C have some different values, but they have to change by the same ratio so that the product 1 over square root LC is always the same, because the resonant frequency is fixed. So the effective capacitance for a 50 ohm transmission line, remember we made a 50 ohm transmission line here, is much lower than, in this case, I mean, this 10 picofarad number was just some arbitrary number I chose, right? This resonant. So if I try to tune this, so if I want to make it narrower, I need to increase the capacitance. So what should I do with Z naught? So if I decrease this, it starts to get sharper. And right now I'm at 25 ohms. Let me pull the limit down to like 1 ohm. So somewhere around there, where it's about 2.5 ohms. That's better. Almost exactly match. Saying 2.1 ohms. So it's saying I have to design a transmission line whose characteristic impedance is 2.1 ohms in order to get the same LC resonator as I have drawn here. So remember that by the fact that the frequency is fixed, the L must also be, the effective L has to be the value I have chosen here. Otherwise, the frequency will not match. But this is completely impractical. 2 ohm transmission lines basically don't exist in most situations. It is not impossible completely to make it, but it's highly impractical, because the kind of capacitance per unit length and you need to this, because this is a low impedance, so it means very high capacitance per unit length is what is required. And that naturally connects with the fact that I needed a large capacitance to come out of the transmission line. The reason is that the typical transmission lines we have looked at, their capacitance per unit length for reasonable dimensions is never going to be in this range. You can almost think of this is that only kind of transmission line which might come close to it is really 2 parallel plates, which are very close to each other, so that you can get a high specific capacitance. Anything which is planar, where the capacitance is sort of coming by proximity and field lines going through the dielectric, it's never going to give you anything in this range. In fact, it's sort of a rule of thumb that anything less than 20 ohms and anything greater than 90 or 100 ohms is not a practical design. On the other end also, we have this problem that if you want now very low capacitance per unit length and very high inductance, then the lines become very narrow. And then they also, in some sense, they sort of don't stop seeing the ground plane, and then they can just be like a piece of antenna which is radiating energy into free space. That is also a problem, because you don't want the energy from the transmission line to be radiating into free space and this, I mean, because that will be a form of a loss in the transmission line. So when it comes to designing transmission line resonators, you are sort of restricted to roughly 20 to 100 ohms. Even with the extreme ends, not so great. Or essentially 50 ohm transmission lines or somewhere nearby is what we get. So does it mean that I cannot make high Q resonators at all? Because in this picture, I don't have too much freedom.
You can play with the length of the time.
So that will change my frequency. I want to keep the same frequency, right? So I've decided I'm going to make it at 6 gigahertz. I've decided I'm going to tried with a lambda by 4. We could check one thing that, if you don't worry too much about the fact that lambda by 2 is slightly longer, we can check what happens if one uses a lambda by 2 resonator and I make this end open. So remember, that will also give me the same resonant frequency. Now, if I look at this graph, now 2.1 ohms is actually giving me a narrower one. So your suggestion is correct to this extent, but how much did we gain? I can now go back and adjust the tuner. 4.2, right? It's almost exactly a factor of, and that roughly makes sense, right? Because you have twice the length now. For the same capacitance per unit length, the total capacitance is effectively. But again, this need not always be correct, because as I was telling you, the effective capacitance is not capacitance per unit length multiplied by length. There is a pre-factor which comes from the fact that the electric field is not the same everywhere, right? It's zero at the short circuit and it's maximum at the other circuits. So you have to consider that field distribution. But I guess between lambda by 4 and lambda by 2, there is not that much of a difference in that pre-factor. But this almost only bought you a factor of 2. But that's not nearly enough. Let's actually check whether this continues to work if we do make it longer. Now, what's the price you're going to pay is that you're no longer going to be working on the fundamental mode. So remember, this is the lowest frequency resonance for this circuit. There is no other frequency mode below it. There are higher ones. We saw that for lambda by 4, after 6 gigahertz, there was one at 18. So for this one, there will be one at 12. But I want the resonance at 6. So I could design a lambda by 2 whose fundamental is at 3 and then look at the 6 gigahertz resonance. Okay. So that's very easy. I can just go here and I can make this lambda by 2 at 3 gigahertz. So effectively, I have doubled the length. That's what this means. And if I come here, and it does seem to work, right? So if I now adjust the impedance again, but it's still scaling quite nice. So I'm 8.4. So I am able to get more and more effective capacitance. But now the price I pay is that the transmission line is very long. And I'm no longer at the fundamental resonance, which means that I'm going to have other modes nearby. Right? So when I was at 6, the nearest mode was when it was lambda by 2 at 6 gigahertz. The next mode was at 12. So 6 gigahertz away and nothing on the lower side. Now, lambda by 2 is at 3 gigahertz. I'm interested in the 6 gigahertz mode. But now the next resonance I'm going to find is actually going to be at 9. So you're now sandwiched between a 3 and the 9 gigahertz mode as well. And if you keep pushing this, this will keep working. And you can make it longer and longer, and you're working at some nth harmonic of the fundamental. But you will now, everything will become closer and closer. So there will be many modes. There might be modes 100 megahertz away. But this idea of getting effective capacitance, the way you suggested, is correct, as long as you don't worry about these other facts and the fact that you have to make a much longer transmission line. So from a practical point of view, much longer transmission line means more things can go wrong. Effectively, if your transmission lines have finite loss per unit length, it's going to be lossier because you have a longer length of propagation between the two ends. So those things will start affecting. So in order to make high Q resonators using this, you have to do something else. So let's just go back to the standard design. Push this back to 6. And let me put it back to 50. Back to this broad response. What you need to do is to reduce the coupling of this resonator. So remember, the resonator is basically that just this transmission line with these two boundary conditions. The problem is that the boundary condition on the right side, which is an open, it's a very strong boundary condition. But on the left side, it's actually just a 50 ohm transmission line. And this is a 50 ohm load, and this is a 50 ohm transmission line. So in some sense, there is really not much of a impedance mismatch going on between these two. So it's not a very good mirror, if you look in the optics picture. So what we want to do is to put something else here. And the simplest something else you can do is a capacitor. And a capacitor which is actually small. So let's say 0.1 picofarad, we can start from it. So what this is doing now is that this capacitor now acts like a partially transmitting mirror. The transparency of that mirror is related to the capacitance or indirectly the impedance. So how does that work? The smaller the capacitance, the larger the impedance, which means more strongly. So if you imagine if this goes to the limit of infinity, then this becomes a perfect open, right? If this is very large, then it directly connects to 50 ohms. So anything in between, you get partial reflection and partial transmission through this. So this is now able to control how much of the energy that might be stored in the resonator can leak out into this 50 ohm environment. So that is basically what Q is a measure of, right? Total dissipation seen by this. Since there is no internal dissipation, then so what did you not understand? But what aspect of it? That why it's partial? That why it's partial? So we go back to our multi-reflection picture we had seen for even a lambda by 4 transformer. At this end, it's a perfect open, so it's going to reflect with a reflection coefficient gamma equals 1. So whatever wave propagates this way, it reflects back. Now the wave which is coming from right to left and it reaches this capacitor. If this capacitor was very, very large, essentially 1 over omega c would be 0. So that's the same as being directly connected to this 50 ohm transmission line. But if it is very small, it's going to see a big impedance. So that means there is going to be a reflection coefficient at this point of, which is basically going to be related to the Z0, which is of the transmission line, and the total impedance seen with respect to this point, which is what? It is basically a series sum of the capacitance and the 50 ohm. So that's going to give you a reflection coefficient. And that reflection coefficient, if it is at high, which means almost all of the power is being reflected back, then that's a weakly transmitting mirror, which basically just means transmission coefficient is small, and vice versa. So the smaller the transmission coefficient, the stronger is the reflection and confinement, which means less dissipation, because which is the energy which is actually going to be dissipated is the part which is transmitted, right? So small capacitance, high impedance, more reflection, less dissipation, and hence high Q. The fact that there is a resonant frequency, that is just related to the round trip time and how which frequencies the waves are interfering constructively after multiple bounces, right? That's the standard parameter. But the transparency of this thing is connected by this capacitance. But this picture, it's not exactly 100% analogous to the situation in optics. In fact, I don't really know the picture in optics that well, because it has some other effects. We will see that in just a second. So let's now look at this graph. So now the pink one is the lambda by 4 resonator with the input coupling capacitor. What has happened here?
There is only phase change and
So two things, right? The position here is shifted. If we now identify this as the resonant, because in this case this was the resonant, and it seems to have gotten inverted in phase, because now minus become plus, plus become minus. There is some little asymmetry here as well. Now all of this is due to the capacitance. Let's first look at so the line width has become narrow, which is what was the only effect we were hoping to achieve with this. The effect of the shift of the frequency is sort of a loading effect, that this capacitance actually becomes part of the resonator. This is, I guess it's sure most of you have never studied this in mechanical acoustics. Did anybody have ever any like these kind of resonances in acoustic waves in undergraduate? Probably, I think these things are never taught these days. So this is actually, in the sound case, it's interpreted as not a very hard boundary condition. So the actual length of the tube, in acoustics, looks effectively longer because the waves actually go beyond the end of the tube into the air a little bit and then reflect back. So this is sort of like that, but in the electrical domain. The effective length of the resonator sort of now looks longer. Or in the equivalent picture, you can actually model this capacitance as just adding to the total capacitance of the effective LC circuit. The effective LC circuit is the one which we saw last time, and what is the formulas are given in COSA, right? So that's the reason for the frequency shift. The narrowing we already know. The asymmetry is related to the fact that the capacitor's impedance is not a fixed value. It is 1 over omega c. So there is actually a frequency change as well as you're going to from here to here. That affects the interference condition slightly, and you don't get a perfect looking resonator like that. But it doesn't matter as long as you're slow. In fact, the reason this asymmetry is so pronounced is that the capacitance value is actually still too high for a typical situation you would encounter, because this line width is still too much. It's like this is 5.598 to 5.712. So that's like 114 megahertz. In this picture, that's still considered fairly low, because Q factor here would be, so this is about 100 megahertz. Resonance is at 6,000 megahertz. So it's like 60. Right? That's not a very high Q. So usually people are trying to make Qs of 1 million and higher for the kind of applications one using, or at least in the few thousand or a few hundreds as well. So if you reduce the capacitance, then this approximation, basically everything happens over a much narrower range of frequency, so it looks more and more ideal. Let me tune this capacitor. So now you see that if I increase the capacitance, the frequency goes further lower, the asymmetry is enhanced. And if I do it the other way around, then it starts to look better and better. This right now is basically a resolution issue, so I need to zoom in more. We're almost close. So it's now it's starting to look nice and symmetric. The thing you can never do is get it back to 6 gigahertz. Because you always need some finite capacitance, so the frequency is always going to be 0. So which means that in reality, if you wanted a 6 gigahertz resonator, you had to choose a lambda by 2, which corresponds to slightly higher frequency. So that with this capacitor, it will come down to 6 gigahertz. So if I now just extend this. Tune this 6, it's now 6.1. So that is entirely a function of the capacitor. Usually, because you're trying to make high Q resonators, the capacitor is going to be small, the shift is going to be small. But you have to keep that in mind when you design your device. If you want it to be 6, you have to design it slightly higher. And these are the things you would check in a simulation so that you can then design the correct coupling capacitor at the right then on transmission line.
So we are connecting something to the port and port. We will have some capacitance at that point, right?
When you connect,
I mean, let's say I am connecting transmission line to a port.
by port meaning like on
On the device I'm connected.
yeah.
So that capacitance will do that and the single curve or
No. So ideally speaking, any such connections should not have any significant capacitance or inductances because you're trying to maintain the 50 ohm nature of that. This capacitance usually will be designed on the chip itself. So if you're making a transmission line, you will make it of the right length and right next to it will be the capacitance. In fact, it is nothing but just a gap in the transmission line. So no, but let me draw what it would look like. So let's consider microstrip geometry, right? So transmission line in a microstrip geometry is just a strip. On the right side, I want an open. So you have to imagine this on top of a dielectric. It's ground. On the right side, I want an open. So how do I make an open? I just leave it. Even though it's not always ideal, but that's the best you can do. And then I want to put a capacitance on this side between some incoming transmission line or my port. But the way you would normally do it is that, in fact, if this microstrip is designed to be 50 ohms, then you just have another line and just put a small gap there. And the distance between this gap will determine how much capacitance you get. If the width of these transmission lines is not big enough to give you a lot of capacity, then you can do other kinds of tricks where you can have these kind of structures. Integrated capacitors. You basically create more area, or you can even make an overlap capacitor by putting something connecting the two and having some dielectric, these overlapping. So you make like a parallel plate capacitor if you need high capacitance, but that's usually not the case because you're always trying to make low capacitance. But this might happen under some circumstances. So The connection you're talking about is that now this, so remember that this is now your 50 ohm feed line. This is where you're bringing your signals in and out. This part is your 50 ohm transmission line, but that is part of the lambda by 2 resonator. But I need to now connect this to something, right? So this will normally sit inside a box, which will have some kind of a metallic wall on one side. And then there will be a connector here, some kind of a coaxial connector, which will have a center pin and an outer conductor. It's sort of like a coax. So that center pin will come out here, and then we make the connection here. And then this is going to be connected to another SMA connector, which has a cable and it goes to the instrument. So all of these connections from this cable, which is a 50 ohm cable, to this male SMA connector, which is a 50 ohm connector, to this female connector, which is actually allowing you to launch onto the microstrip. All of this should ideally look like a long transmission line which ends at this point, and equal to 50 ohms characteristics. In practice, every such joint will have some small amount of reflection happening, but if it is designed properly, then that effect will be very small. You are not going to get this kind of an effect.
The capacitance will also be very small, and if capacitance is small, then reflection will be also very high. Right? I mean,
no, but what type of capacitance? That the capacitance in these kind of connections, the only capacitance you can get is between the center pin and ground, not between the pin and the pin. That would be called a bad connection, and you can do that. You can intentionally make a bad connection and you can create a resonator. Check this. Hello? I think I have a Yeah, so we are trying to make metallic contacts between these things, right? So the RF part is more complicated than just doing a simple wire-to-wire contact, because it's not just about getting the contacts or getting the geometry correctly so that the waves are propagating and then not experiencing any impedance mismatch at any of these connections. So if you wanted a series capacitance, then you need a break. That's just terrible, right? I mean, you won't do that, but you can, and in fact, you can see this sometimes when you're measuring in a vector network analyzer, that while you are connecting the cable, there will be a particular time where the pins would be very close to each other and not fully connected, and you will see a resonance peak show. Because at that point, the capacitance would be just right to give you, but it will be like a momentum. You can do it, you can play around by loosening the nut and creating a resonator like that. That's not going to be stable. This, when you design, you want the Q to be very, very stable, so you design it on chip, or with the lump element capacitor, you require to do that. But usually, these kind of capacitors are almost always made as a gap or an interdigitated kind of capacitor. Okay. So, and then finally the phase change is just because of the capacitance is giving an extra reflection coefficient of the opposite sign. That doesn't really change anything about whether it's a parallel LC. It's still a parallel LC oscillator. Just there's an overall phase shift that has no consequence because you can always add a negative sign. So which also means that if I look at this thing in phase, you will see it will look different. So here. So you see the blue one is the parallel LC oscillator, the standard one, and that has the usual, plus 180 to minus 180 kind of curve. This one is different. It goes from 0 down and then flips around. We have seen this before, but this again is just a question of phase wrapping. I can do this angle wrap, and then this means that there's an extra overall phase shift because of the capacity. Now, these kind of things can also be done here. If you have a lumped element parallel LC oscillator, the quality factor for a circuit like this, which is directly coupled to the 50 ohm line, is only dependent on this 50 ohms, the frequency, and this capacitance. So it's impossible to make very high Q resonators of this type with the circuit, because then you need capacitance to be huge. Right? That's the only, if you want 100 times more Q, you have to make the capacitance 100 times larger and the inductance 100 times smaller. So then those values will become unreasonable. So there was a constraint in the transmission line that I said the characteristic impedances can only go from 20 to 100, and that sets some limit on the effective capacitance and inductances you can get for your effective LC resonator. Here also in realistic terms, you cannot get arbitrarily large capacitors. I mean, you might say, yes, 1000 picofarad to milta hai, bade mote aate hain, but wo microwave frequency mein is not going to work, right? So you cannot have large capacitances and large inductances also, particularly even if you're using lump element, making large capacitance and large inductance is very hard at microwave frequencies. So even for lump element circuits, if there is some particular need and you want high Q, you can do the same trick. You just put a series capacitor here, and it works in exactly the same way. Right? So this is one resonator, which is some lambda by 4 section. You can think of that, and then you put a capacitor here. Right? Here, of course, there is no picture of waves multiple bouncing, but the two are completely equivalent pictures. So what is happening now is that the this resonator is dissipating through a resistor which is now being modified by the presence of the series capacitor. So if you have a small capacitor in series with a resistor, then it will appear as a much bigger resistor in parallel. So R goes up, Q goes up. So that's the alternate picture one uses for this. Now, coming back to this, all you had to create was some kind of an impedance mismatch, right? So you can do that with an inductor as well, or some other combination of inductors and capacitors, as long as it is giving you the right impedance at the relevant frequency of interest. This would work fine. You can also play with the Z0 to some extent, which is allowed, within this 20 to 100 ohm range, and that will also affect your Q factor. So if I now look at the same resonance, let me go back to here. Ohms. I am now increasing the Z naught, and in fact that also changes the frequency. So anyone apart from Panya can you explain why this is happening? I'm not changing the length, right? I'm only changing the characteristic impedance of the transmission line, which I have is this one, has a coupling capacitor at the input, and I'm changing the characteristic impedance here, and that is affecting the frequency of the resonance. Should this happen? Well, I mean, I guess it all trust microwave office, so it should happen. Why does it happen?
The transmission line also have its internal capacitance, I think, with J not that was
Yes.
that is where we're getting some.
Can you be more precise? Let me do something. What did I do? I'm forgetting that you guys can still see the screen even if I don't share. I'm going to just short circuit the capacitor so that it's not there. Now, the resonance, of course, becomes very broad. Remember that when we were in this position earlier, I changed the characteristic impedance and I showed you it only got narrower. Right now, the frequency is off because I changed it. So here it's got it back to exactly 6. Now I've brought it to like 4.9 ohms, and the resonant frequency is rock solid.
So here, the A and C both are determining Z naught, and when you are fixing Z naught, then A and C are I mean changing simultaneous so that frequency is changed, and that's why I think that it is good. But
Yeah.
And Q factor depends on.
No, the Q factor part, that was the part we already discussed. So we know that now the Q factor is becoming better because if I go to low impedance, the effective capacitance is higher. So then RC omega plasma, which is the Q factor. My point is here when I change the characteristic impedance, the resonant frequency did not change. But here, if I introduce the coupling capacitor, then the frequency seems to depend on the characteristic impedance as well.
Okay, so when we are introducing that capacitance, the effective capacitance will be some combination of the external capacitance and the internal capacitance. But L will be similar. And
Exactly. So because now the total resonant frequency is a combination of L, C plus C external, that balance is no longer maintained because the balance is maintained between only the L and the C. So because there's an extra capacitance, depending on how much extra this capacitance is in relationship with the original capacitance, it will affect the frequency as well. So that's just what you were saying earlier was also sort of correct if one took a leap of faith. But the precise statement is because now the total resonant frequencies depend on the combination of both the external capacitance and the capacitance contributed by the second transmission line. So when you change that, you get frequencies. So this is again something you have to keep in mind when you are designing devices. Because you design some coupling capacitor, then later on you decided to change the characteristic impedance, you have to redesign the coupling capacitor to ensure or adjust the length to get the same frequency and also to get the right Q factor. Because the Q factor will also change because the total capacitance will now be different if the Z naught is different and the effective dissipation can change as well.
Just to confirm,
Yeah.
only around resonance, we can say that C sec, whatever C effective is there, the C coupling, which is in series, is effectively like that.
Yes, only at resonance frequency, around resonance. Anyway, I mean, even if things are changing, if the resonant frequency is changing, then it's at a new frequency, and the transparencies will change. So if you use the same coupling capacitor for a 6 gigahertz resonator versus a 3 gigahertz resonator, it will give you different Q. Because the transparency 1 over omega C is going to be different at those different frequencies. But this simple model that you can this RC can be rewritten as some R prime and C prime, which turns out to be C. So this C prime now, so here was your resonator with its LC. So now this adds in series in parallel to the capacitance, so increases the total capacitance. And this R prime is going to be much greater than R, so reduces the distance. All right. So all of these ideas can be extended to lambda by 4 transmission lines as well, lambda by 2 transmission lines, or if you're working at much higher harmonic modes. You can also make this not out of a capacitor, but out of an inductor.
That is.
Well, you can do many different things. The problem is about what is the practical thing to do. Since for making a good reflective mirror, you need a small capacitance, and small capacitances are easy to do. Right? If I decided to use an inductor here instead, remember I need high impedance for it to work as a good mirror. And high impedance for an inductor would mean high inductance. Now that is opposite to what is easy to do in the thing. But it's not, I mean, it will, if I, in microwave, of course, everything can be modeled perfectly. This will, work. Right? 100 nanohenry, in fact, it has made it quite sharp. But look what happened to the frequency. Shifted to the other side. That also makes sense if instead of an inductor, I had an inductor in parallel, 2 parallel inductors will reduce the inductance, so the frequency goes up. But here you need a much larger inductance. So one can actually do something clever here, is not to put it in series, but to put it in parallel to ground. Maybe this might appear strange, but essentially it's doing the same thing. That it's creating an impedance mismatch point here. So the waves which appear here, they will see some impedance which is not 50 ohms. Right? So that will cause a reflection. But now you don't want this inductance to be too big either. So you have to see whether that actually works out for this. So because basically a very large inductor means it's almost not there. It's connected directly. By now tune this Oh, actually, sorry, I made a mistake here. Can someone tell me why this is not a good boundary condition for this particular resonator?
This goes like one gap scope, the other is kind of trying to make it.
So the problem is that we were working with a lambda by 2 resonator with both ends which have to appear as open. This inductance to ground is more naturally a short circuit. So it will behave better if this was a lambda by 4 resonator. So I will not be able to find a good value of L, which gives me good reflection, but at the same time retains the lambda by 2 nature of that. Okay, so not all combinations are always possible. So that's why this doesn't work. But this will work for 90 degrees. Let's see that. As small as possible so that space for short circuit. The inductor was too big to give you over. So you wanted to make it a short circuit, but
Five, five, and 4.10 was of that, from 20.
yeah, it's too big an impedance. Yeah, since we wanted a short boundary condition, it had to be a much lower inductance, and then the frequency shows up. Okay, I'll just go on for 10 more minutes and then stop. Very short, very brief thing about the. So I just want to very quickly mention this about microwave cavities, which can actually be made as cavities. Okay, that's one of the. So I don't know, like in our group, because of use all of these things, we use all the words interchangeably. Resonator, LC oscillator, cavity, everything means the same thing for us. But if you look at the name here, it says waveguide cavity resonator. So cavity here literally means there has to be a hole somewhere. So one of the standard ways of making such a system is just a space of air which is covered, surrounded by metallic boundary conditions in a rectangle or cuboid geometry. So at the ends, the electric field has to go to zero. The um, parallel component. So if you think about TEM modes in these or TE modes in these systems, then these boundary conditions will set up the conditions for having standing waves. So here is one example shown here where they're saying this is the field variations for TE101 and 102 nodes. So now there are two dimensions where the standing waves are set up. So you see there's one standing wave going in this direction, and then there is a standing wave going in this direction. Both of those have to be satisfied for the resonant frequencies. So the resonant frequencies of these things are controlled by both these dimensions, these two dimensions. The third dimension, because this is 101 mode, that actually doesn't play any role. The electric field there doesn't vary in that direction. So there's no variation of electric field between this plane and that plane. So the electric field always points in that direction. So this again for in the kind of experiments we do, it's a very standard design we use, and I have some cavities here to show. But this is just one way. They can, and all of this concept of loaded Q, unloaded Q also works here. How does one actually measure this? This looks like a box which is completely closed from all sides. So usually you have to make some kind of an aperture and bring in some probe to excite them. And that now allows the energy inside this cavity to leak out. Okay, so that's the loading part. That is going to be connected. And because it's just some pins sticking in, you have to model it as a 50 ohm resistance with some effective capacitance which is connected to this resistor. So even these kind of resonances can be modeled with an effective LC model at the resonant frequency. You have some effective L and effective C. And this typical ratio of L's and C will be different than the ones you achieve using transmission line. Because here these fields are propagating mostly in vacuum or air. Whereas in your transmission lines, they were on a substrate, so there was some finite direct. So can you guess, will the effective L's and C's, how will they change with respect for a 3D waveguide cavity like this as compared to, say, a transmission line one? Will the capacitance be higher, lower, same? Lower capacitance, just because dielectric is essentially vacuum dielectric. So you can get different effective capacitance. So that's also how the introduction of a pin will pull the frequency will also change. Because the internal capacitance is very small, the external capacitance starts to have a bigger effect on how much it gets. Yeah.
So saying this for 3D structure can be modeled as
Yes. 3D structure has no meaning. The fact that it's 3D is just a detail. The fact that there is a resonance at that particular frequency, where if you now put some excitation code, then with respect to that, it will look like an ideal resonance, which can be modeled by LC. But again, the details of what happens away from the resonant frequency will be different. So this will also be different for a transmission line resonator and a waveguide resonator. You can design them, both of them, to have the same LC values. So which means not just the frequency is the same, but the ratio of L and C is also the same. You can do that, but as you go away from the frequency, resonant frequency, how that will change need not be the same, because that depends on exactly what the structure is. But these kind of effects you can model in a finite element simulation. And this is not the only shape, any shape which gives you boundary conditions, and that will of course change the. So here you can have circular or cylindrical waveguide resonators. Even a perfect sphere can be a resonator. The modes are going to have different shape. You can also just have a slab of dielectric Right? So here we said it's vacuum, where the boundary condition is all because of the magnet. But if you just have a solid piece of a dielectric, let's say a high dielectric constant material, then the fact that at the edge of the dielectric you are moving from high dielectric constant to air, that is also a boundary condition. Right? So that gives a mechanism for the waves to reflect, and then you can set up standard waves. So those are also other ways of creating. So this also talks about dielectric resonance. In fact, these are some standard ways people make some of these what they're crystal oscillators or something like that. So this section talks about this excitation, which we've already discussed briefly about. So this is the gap I was talking about, to create between the field line and the section of transition. So let me show you this hit the lines. So this is an example of this rectangular waveguide. Of course, we need a way to get into it. Otherwise, first of all, machining something which is completely hollow on the inside is impossible. So we make it in two pieces, and then we just close them together. So once they are closed tightly, then inside you have a closed volume. These two dimensions, this dimension and the dimension coming out this way, those are the two relevant dimensions for the TE mode. So remember it said TE101. So the 01 is the shortest dimension. So this length doesn't matter in determining the resonant frequency, but this length and the depth of this cavity determines the electric field, the resonant frequency. The material will decide how much internal losses you want to come. The operating temperature will decide. This is aluminum. It will have a very different Q factor at room temperature versus at very low temperatures, where in our lab we do our experiments when it becomes superconducting. If this was made out of copper, it will not change so much between room temperature and have a different value. A lot also depends on the surface finish, how the polishing is done, and if there's any contaminants left as well. You can also see how the signal is coming in to this cavity. Right? So this is the coaxial connector, which basically you can just think of this as a coax. And then on the inside, there is a small hole. I will pass this around, you can see. You can actually, the pin is not visible because the pin has been chosen to have a certain length that it's not even entering the cavity. But because there is a hole, there is some field line coupling to it. Because that is just because of the choice of how much coupling to the external mode we want. That's how you tune it. So what I mean is that there is a, so if I look at this profile, there's my cavity and there is a wall thickness here. So here there is actually a hole. And this connector is like this, and the center pin comes here and maybe it only stops up to this point. You could have extended this here, but maybe that was too strong a coupling in this case, or maybe the pin fell off. I'm not really sure what the case is, but you can keep it like this. Now, there is another catch here that if there was no pin, actually this diameter of the hole, this is now like a circular waveguide. That has a cutoff frequency, which is going to be related to the circumference of this hole. So this hole is small and long, then waves actually cannot couple out of this. You will get some evanescent decay happening here. And if it is long enough, you can actually have a hole and it will not matter to the cavity. The boundary condition will still be the same as if this hole was not there. But if you now stick a pin in, and the pin is only extending up here, then what happens is that from the location of the pin, you have a TEM mode which can propagate because that is like a coaxial mode. So this pin can tap into the decaying evanescent, which is non-propagating mode, and then couple the signal out. So you can get coupling out through this mode, even if the pin is not all the way into the cavity. Whereas if you don't have the pin at all, then this waveguide cannot propagate any signal because it's a different mode of propagation. That's a circular waveguide with a cutoff frequency, which is much higher than the frequency we are interested in for the resonance. But sticking the pin in causes you to tap into the evanescent field, and then it can excite a TEM mode which can be coupled. Okay. So this is one thing I just remembered something about when I was discussing this hole. There was actually a successfully built cavity. In fact, I also made this comment that how will I machine a piece of block like this without having access? How do I make this from the inside? So one particular research team in Chicago figured out that because these holes don't matter, they just put lots of holes, which are spaced closed apart from different angles, so that effectively inside there is a continuous volume of open space, but it only has these very narrow openings to the outside. So the narrow openings allow a way to get in to drill a hole internally. And this they did by putting holes from like opposite sides, which are slightly offset, so that every hole is different, but between them where they meet, inside a larger hole opens up, and then you have a continuous cavity. The reason for doing that was they are trying to minimize the losses of the cavity, and one loss comes from the fact that these are two pieces, and when you join them, there are actually currents which flow from one side to the other side, and that interface can have some kind of lamination and give some kind of a resistance to the path of the current. So they wanted to make a cavity which has no joints. So this was a very clever way of doing this. It actually looks crazy when you look at the device. I'll see if I can find the picture and send it to you. So there are, those are some specific tricks, but let me pass this around and see how that looks like. And then finally, I want to show that these ideas of a two-dimensional planar resonator and this three-dimensional cavity, it's actually a continuous spectrum. You can combine two of these ideas together and make something like this, which actually is you can call this a 3D CPW, or you can call it a 2D coax, somewhere in between. Okay. So what it actually is that there's actually too much stuff going on, but just focus on this part here, like you see these four things that are sticking out on. So let me draw that here. So there is a circle here. This is sort of not relevant for our discussion, but there is this structure here, which looks like this. Okay, all of this is metal. This is a λ/4 resonator. Why? This here is shorted. So if you think of this as a CPW line, here's the central line. Here are the two ground planes, right? Then this is the direction of the transmission line. At this end, the ground metal comes around and then it's connected to the central line. So it's a short circuit, right? So this is your shorted end of the λ/4 line. And on this side, it doesn't go all the way. There's a little gap here. So this is the open part of the λ/4 section. So this now supports a λ/4 mode, but this is sort of a three-dimensional version because there is actually this part is actually machined separately. I can take that off, and then here is just a piece of cavity. Okay, so and then there is a similar piece on top which covers the whole thing. So if you now look at what this thing looks like, it looks like a rectangular box with a central pin sticking from one edge, which is the shorter end, and it's open on the other side. So what do I call it? From the top, it looks like a CPW line, but there's a third dimension. If I consider the fact that it's enclosed from metal from all sides, then it looks like a coaxial line, right? It's the ground on all sides, but the central line is not circular, right? I have made this planar thing. So those things will affect the details of exactly how the mode will propagate, but this will support a TEM transmission line. Okay. And the rest of the circuit is actually also a very long network of transmission line. It's this central ring here is a circular CPW transmission line, which is wrapped around itself. So ignore the bottom part. This is just a circular central line, and there is metal on both sides. So this is all metal, this is all metal, and this is metal. So it's a CPW line, right? But again, in this three-dimensional coax type of version, and this is a transmission line resonator with periodic boundary conditions. Unlike the ones we looked at so far, which either had, a short at one end or an open at the other end, and then an open on this end. This is just a transmission line which is wrapped around itself. But that is perfectly fine. You are familiar with this kind of periodic boundary conditions in physics, right? Electron orbits, you know that the wavelength has to be an infinity multiple of the circumference. Exactly the same argument applies here. So one wavelength, the lowest mode is when you just pick any point, because there is no, because it's circularly symmetric, there is no special point to say where is the node and where is the antinode. And this is actually one important difference, that you cannot really think of them as standing wave modes. These are actually traveling wave modes. But the point is that I start from one point, and let's say that point had 0 voltage, and I go and I come back, and that would be one wavelength. So one wavelength fitting in the entire thing, that's the only way I can come back to the same boundary condition, right? I have to match the boundary condition at any particular point. But this kind of a resonator will have no node or antinode. Every point will have a full variation of voltage or current. But it's the periodic boundary condition which then decides that, okay, only certain modes will survive, and then you will have harmonics. Okay. So you can also pass this around. Just be careful, there are 3 different pieces here. Okay, so I'll stop here. Any questions?